Before we begin, make sure you watch this video all the way to the end, because what we're about to explore completely changes how you think about black holes, time, and the structure of the universe itself. Imagine this. Right now, somewhere in the cosmos, a black hole is spinning at nearly the speed of light. Its rotation is so intense that it drags space-time itself around with it, twisting reality like a cosmic whirlpool. Now imagine that, in a single instant, that rotation just stops. No warning, no slowdown, just silence. What would happen next wouldn't just be dramatic. It would be catastrophic, beautiful, and deeply unsettling. Black holes are not just simple vacuum cleaners in space. Many of them spin, and when they do, they become something far more exotic. A spinning black hole is known as a Kerr black hole, and its rotation creates a region outside the event horizon called the ergosphere. This is where things get weird. Inside the ergosphere, space itself is dragged along with the rotation. Nothing can remain still there, not even light. Everything is forced to move in the direction of the spin. This effect is called frame dragging, and it's one of the most extreme consequences of Einstein's theory of general relativity. If you were somehow able to hover near a spinning black hole, you wouldn't just be pulled inward, you'd also be swept sideways, caught in the flow of space-time itself. Now here's where our question becomes truly fascinating. What if that spinning suddenly stopped? First, we need to understand that stopping a black hole's rotation is not something that should be easy or even possible under normal conditions. Black holes gain their spin from the stars or matter that formed them or fell into them. To stop that spin, you would need to extract an enormous amount of angular momentum. There is actually a theoretical process called the Penrose process that allows energy to be extracted from a rotating black hole, but even that is gradual and complex. What we're imagining here is something far more extreme, an instantaneous halt. If the rotation suddenly ceased, the ergosphere would vanish instantly. That region where space-time is being dragged around would collapse. Any matter or radiation trapped within it would experience a sudden and violent change. Instead of being forced to move along with the spin, everything would find itself in a completely different space-time geometry. The consequences would be chaotic. Particles that were previously in stable or semi-stable orbits due to the black hole's rotation would suddenly lose that balance. Some would fall inward, crossing the event horizon. Others might be flung outward at incredible speeds. Jets of high-energy particles, often seen shooting out from the poles of spinning black holes, could be disrupted or even shut down entirely. These jets are powered in part by the rotation, so removing it would cut off their energy source. Now think about the event horizon itself. In a rotating black hole, the shape of the event horizon is slightly flattened due to the spin. When the rotation stops, the black hole becomes a Schwarzschild black hole, which is perfectly spherical. That means the event horizon would suddenly change shape. This might sound subtle, but on cosmic scales, it's enormous. The boundary of no return would shift, potentially swallowing objects that were previously safe or releasing ones that were on the edge. But the most dramatic effects might not even be visible right away. The sudden change in the black hole's rotation would send ripples through space-time itself. These ripples are known as gravitational waves. We've already detected gravitational waves from black hole mergers, but this would be different. This would be a single object, undergoing a rapid and massive change in its structure. The resulting of gravitational energy would spread outward at the speed of light, carrying information about this bizarre event across the universe. If you were close enough to detect it, you wouldn't just see it, you would feel it, in a sense. Distances would stretch and compress as the wave passed through you. Time itself would seem to wobble. It would be a reminder that space-time is not a fixed stage, but something dynamic and alive. At this point, if you're enjoying this journey into the extreme side of physics, take a moment to like the video, subscribe to the channel, and turn on the notification bell so you don't miss the next deep dive into the universe's strangest phenomena. Now let's go even deeper. What happens to the singularity inside the black hole? The singularity is the point where density becomes infinite and our current understanding of physics breaks down. In a rotating black hole, the singularity is not a point, but a ring. This is known as a ring singularity. The rotation essentially stretches the singularity into a loop. If the black hole suddenly stopped spinning, that ring singularity would have to collapse into a point singularity. This is not just a geometric change. It represents a fundamental shift in the nature of the object. The internal structure of the black hole would be completely reconfigured. And since we don't fully understand what happens inside a black hole anyway, this pushes us even further into the realm of speculation. Some theories suggest that the interior of a rotating black hole could allow for strange paths through spacetime, possibly even connections to other regions of the universe. If the rotation stops, those possibilities might vanish. Any hypothetical pathways or structures supported by the spin would collapse. There's also the question of energy. Where does the rotational energy go? Energy cannot simply disappear. If the black hole loses its spin instantly, that energy must be released somehow. It could be emitted as radiation, gravitational waves, or even converted into high-energy particles. The exact mechanism is unknown, but the amount of energy involved would be staggering, potentially rivaling the output of entire galaxies for a brief moment. And what about the surrounding environment? Black holes are often surrounded by accretion disks, swirling masses of gas and dust that spiral inward. These disks are heavily influenced by the black hole's rotation. The spin affects how close matter can orbit before falling in and how energy is transferred within the disk. If the rotation stops, the structure of the accretion disk would be thrown into chaos. Orbits would shift, collisions would increase, temperatures could spike, as matter is suddenly forced into new configurations. The entire system would become unstable, at least temporarily. Over time, it might settle into a new equilibrium, but the transition would be violent. Let's bring this closer to home, just for a moment. If such an event happened relatively nearby in our galaxy, the effects could be detectable from Earth. We might observe a sudden change in the brightness or behavior of a known black hole system. Telescopes could pick up unusual bursts of radiation. Gravitational wave detectors might register a unique signal unlike anything we've seen before. It would be one of the most important discoveries in the history of science because it would challenge our understanding of fundamental physics. It would force us to rethink how black holes work, how energy is conserved in extreme conditions, and how spacetime responds to sudden changes. And here's the truly mind-bending part. The idea of a black hole suddenly stopping its rotation might not just be a thought experiment. It could hint at new physics. Perhaps there are processes or interactions we don't yet understand that could cause such a change. Maybe in the early universe, under extreme conditions, events like this were more common. Before we wrap up, I want you to think about this and let me know your thoughts in the comments. What do you think would be the most terrifying or fascinating consequence of a black hole suddenly stopping its spin? Would it be the gravitational waves, the collapsing singularity, or the chaos in the surrounding matter? As we come to the end of this exploration, remember that black holes are not just cosmic curiosities. They are laboratories for the most extreme physics in the universe. By imagining scenarios like this, we push the boundaries of our understanding and get one step closer to answering some of the biggest questions in science. If you found this video interesting, make sure to like, subscribe, and turn on the notification bell so you never miss another journey into the unknown.